Good afternoon. I am pleased to introduce Dr. Briony Horgan. Dr. Horgan is an assistant professor of planetary sciences at Purdue. Her research program uses data from NASA satellites and rovers, along with lab and field work back on Earth, to understand geologic history of Mars and the Moon. Professor Horgan is a co-investigator on the Mastcam-Z camera system for NASA's upcoming Mars 2020 rover mission, the first step towards Mars sample return. Today, she will present a talk titled NASA's Search for Life on the Red Planet. Please silence your electronic devices, but don't put them away. We want you tweeting about Mars on the hashtag Dawn or Doom. Please join me in welcoming Dr. Horgan.
Thanks. All right, thank you very much. I'm delighted to be here. Yes, I'm Dr. Briony Horgan, and today we're going to talk all about Mars. Please feel free to interrupt me anytime with questions. I'm happy to field whatever your burning questions about Mars and planetary science and NASA, so whenever you're ready, just raise your hand. All right, so we're going to start off today. Here we have, actually, do we have a laser pointer? Is that something we have? Oh, it's okay. All right, so we don't have a laser pointer, but that's fine. So here is our title shot. This is actually a selfie taken by the Mars Science Laboratory rover, also known as Curiosity. And we'll talk all about Curiosity later in this talk. Oh, wonderful, thank you. Okay, so this is really NASA's story, though. Everything I'm talking about here today is NASA-funded, NASA-developed. Everything here is NASA. And NASA does a lot. NASA does a lot with very little. NASA's budget is very, very small. And here are all the things that NASA does: human space exploration, most Earth-observing satellites funded by the government or funded by NASA, aeronautics research, planetary science we're talking about today is entirely funded by NASA, astronomy, and heliophysics. NASA has a really broad portfolio. It does a lot of things with very little. It's very good at that. But a lot of what drives, especially the science part of NASA, especially planetary science and astronomy, is one burning question. And that is, are we alone? Are we alone in the universe? And so when we think of this question ourselves, what we usually think of is, are we alone? Are there other intelligent life forms? And that's a really important question that NASA is answering with help from places like the SETI Institute to help to look for signs of intelligent life in the universe. But there's a much more fundamental question that we can ask there, and that's, are we alone as life forms on Earth? Is Earth life the only life in the universe, down to even, say, microbes? Are there microbes that exist on other planets? We have no idea right now. We have no way to quantify how common life is, how commonly it starts. And so NASA is trying to come at this not just from looking for intelligent life, but also this much more fundamental question of how commonly does life, even at its most simple form, how commonly does that evolve? And so that brings us to Mars. And today we'll talk all about Mars. And Mars is special in NASA's search for life in the universe because, as I will argue, Mars is currently our best bet for finding signs of life beyond Earth. So why is that? Well, here's a great image showing why. So here we're looking at as the topographic map, an elevation map of a little part of Mars. Here's a 100-kilometer scale bar down here. And you can see this does not look like the moon. If you pulled up a similar map of the moon at this scale, it would just be craters, 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 on top of craters, craters all the way down. Here you can see there's much more complicated geology going on here. And in particular, you'll notice all these feathery patterns going all this direction, turning into these valleys, draining into these craters. These are river networks on Mars, ancient dried up valley networks that we find all over Mars. And these have been argued about quite a bit, but we're pretty sure are direct evidence that water once existed on ancient Mars. So if we look at Mars as a whole, these things are extremely common, these ancient dried up river networks. So here's Mars as we'd see it with a camera, what we call the visible. Here we can look at it. This is an elevation map of Mars. So blue is low, red is high. You can see it sloping like that. And so all these little red dots on here are where we find these valley networks, and Mars is just littered with them. You can see there's sort of this stripe that follows all the way across Mars. So this is evidence that the Mars as a planet as a whole was once much warmer and wetter than it is today. Today it's a very cold, arid, dry place. You can live on it as a human with a lot of help. It's pretty dangerous. You wouldn't expect to find life living at the very surface of Mars today because it's pretty inhospitable at the surface. What's some other evidence that Mars was wet? Well, here's what a river delta looks like that we see on Earth. This is actually from the north coast of Alaska. Here's a river delta on Mars. This is an Eberswalde crater. This is actually A pretty big delta. This is 2 kilometers down here. And what we're seeing here is the record of one of these river networks emptying into a crater lake over a very long period of time. Deltas take a very long time to form. So it's basically you have your river coming in here, hitting a lake, depositing out its sediment load, leaving behind a delta. And that takes a long time. So these things like this, these deltas, are evidence that this warm, wet period on Mars wasn't just a flash in the pan, that it was around for quite some time. So that's the idea. So Mars now, cold, dry, arid, not very hospitable to life, at least to the surface. But if we look at Mars 4 billion years ago, we think it looks very different. This is an artist's conception, very suggestive. There's even some green flecks in here, which you may or may not believe. But we think it's possible, still very contentious, whether or not Mars ever had an ocean. The northern part of Mars is one big basin. It could have hosted an ocean at one point. But we think for sure Mars was, at least to some degree, warmer and wetter to the point where it could support liquid water 4 billion years ago. And here's the really interesting part. This is Earth 4 billion years ago. This is a very important time in Earth's history, because this is right around the time when Earth was developing life for the first time, right around 4 billion years ago, maybe give or take a bit. But the problem is, we're trying to understand the origin of life, the evolution of very early life. We don't have a good rock record of that period in Earth's history. It's all been destroyed by plate tectonics. Plate tectonics are the evolutionary biologist's bane in a lot of ways, because it's taken all that rock, it's destroyed it, crushed it up, so it's really hard to read now to look for signs of life. What's great about Mars, Mars has never had plate tectonics as far as we know. Again, that's controversial, but we don't think it did. We do know for sure that there are tons and tons of areas on Mars that date from this same time period that have evidence for water that may or may not also have hosted life. So Mars is a place where we can go to learn about this early period on the Earth. So in some ways, Mars is an analog for the very, very early history of the Earth. All right, so Mars. So that's the argument. Mars is currently our best bet for finding signs of life beyond Earth. NASA is not just looking at Mars, even within our solar system. There are places like Europa, a very icy moon of Jupiter, which we think hosts a modern subsurface ocean. And that's a very exciting place. NASA is actually about to launch, in a few years from now, a flagship big mission to study Europa and to help us understand whether or not it might host modern life. But it's really hard. And this is another advantage of Mars. The environments we're talking about for Mars are Earth-like. They're the same kinds of places, rivers, lakes, deltas, hot springs, all kinds of things that we have on Earth, and we know how to study them. Europa is really interesting, but it's a completely alien environment, and that makes it much more difficult to study. And it's also really hard to get to that ocean beneath the icy shell. So NASA's working on that, but right now the big push has been for Mars, because we think we know how to study it and how to look for life on it. Okay. So this idea that Mars is an excellent place to look for life, to learn about the early Earth, has motivated, now we're going on almost 60 years of exploration of Mars. And so here's what we like to call the Mars exploration family portrait, all of the spacecraft from all the different countries that have explored Mars. And here you can see these are mostly satellites or orbiters. We have a few select special robots that have explored the surface of Mars. And so we've actually looked for life on Mars before. This isn't a new thing we're trying to do. The first valley networks were identified clearly kind of in the late 60s, early 70s from orbital imagery of Mars. And the Viking landers were sent in the late 70s to look for life on Mars, to actually sample and look for extant modern living life on Mars. This is one of the founding fathers of planetary science, Carl Sagan, inspired this whole generation of planetary scientists. Also one of the main scientists on the Viking mission. So Viking, you have to think about the time this was at. This was in the late 70s. We'd never landed a really capable spacecraft on Mars before. We had really no idea what this was going to find. They picked the landing site from orbit as the lander was spinning around in orbit and the orbiter was taking images. These were completely new views of Mars. So when this thing landed, there were senior scientists in the room that will begrudgingly admit they were not entirely sure that the first pictures wouldn't show little green men or palm fronds waving in the wind once they landed. But they didn't. So this is what one of the landers looked like. So they landed in the vast northern plains of Mars, very flat, very easy to land on. Engineers really like landing in parking lots. But so Viking, its main goal was to sample the soils at these far northern sites and to look for life. And so it did that a couple of different ways. They sampled the soils and mixed it with nutrients and looked to see if there were any reactions inside the soils. You know, gases given off, other stuff that might indicate that life was eating up those nutrients. Those experiments were actually positive. That something happened when they added those nutrients to the soils. But then they went and looked at the soil and analyzed it for organics, and as far as we know, life is based on organic matter, and they didn't see anything. And so it was decided that no, that first experiment had to be wrong, we were seeing something else, it couldn't be true. Now we've actually flipped our interpretation, that first experiment that showed that there was life metabolizing things may have actually just been oxidizing materials in the soil that reacted with the nutrients. But we also now think that Viking detected organics in the soils. That same oxidant that got in there and messed up that first experiment actually destroys organics when you heat them up in the kind of experiments that we do, mass spectroscopy, for example, to look for them. So based on later missions, we now think Viking detected organics. Whether or not detected actual extant life is an open question. Very controversial. But that brings us to the modern Mars exploration program. And this is a much more careful program than Viking was like just one shot, let's just see what's there. NASA's modern Mars exploration program is one step at a time, and there are 3 key steps that we're working on. So the first is follow the water, and this was the mantra at NASA for a very long time. Follow the water. We know water is necessary for life. That's the one thing we think we know. You need a solvent. Water is a great one. We think life requires water. So if we follow the water, that'll get us closer to looking for life. Next, once you know where the water is, find a habitable environment. So not just water, but somewhere that microbes or whatever life could live in. So there's chemistry, there's an energy source, something that could help life survive and thrive. And then finally, once you've done that, once you know the kinds of environments where life might have lived on whatever place you're looking at, Mars, Europa, etc., then you can look for signs of life. And that's the next big step. So, but this Mars exploration program spawned the Era of Rovers, and this really extends beyond 1997. The Sojourner Rover was part of the Pathfinder mission. It was really a technological demonstration that we could, in fact, send a semi-autonomous roving robot to another planet and have it be able to find its way around rocks by itself and explore a little area. After that, we get into the modern Mars exploration program, and that's really talking about the Spirit and Opportunity rovers, shown here, very human size and scale, and then the Curiosity rover, as well as the upcoming Mars 2020 rover, which will look very similar to Curiosity. So this is our rover family portrait. This is actually taken in the Mars Yard, the Jet Propulsion Laboratory, where they do a lot of actual testing of rover analog robots to see how they handle different terrains. So here's the problem, though. Mars is hard. Mars is a really hard place to get to. Here's a great graphic I love that shows all the missions from Mars to Mars starting about 1960. All the red in here are the Soviet missions over here. And so these circles in here, this is missions that flew by Mars, missions that orbited Mars, missions that landed on Mars, and then missions that roved on Mars, actually. But this line back here, that's mission failure. Mars is really hard. That's what all of these circles back here are telling us. It is hard to get to Mars. It is really hard to land on Mars. And people have had a very hard time. One thing we're very, very proud of in NASA is that NASA's had excellent success in the past 20 years or so, after a few blips back here that were a big deal at the time. But NASA's been doing really well with this, and we're very, very proud of our engineers for getting us this far. So keep that in mind. Mars is really hard. Okay, let's start with the Mars Exploration Rover, Spirit and Opportunity. These are, in my opinion, some of the cutest robots to ever have roved. But these are what we like to call robotic field geologists. These rovers were designed to be very much at the human scale. They have 2 eyes that have the same kind of resolution and depth perception that humans do, and at the same height, they're about my size, more or less. Their arm on down here, actually, it has the same dimensions and ratios and things as a human arm, so it could actually act like an arm and poke rocks and sample rocks and drill rocks, just like a robotic geologist does. It even has a little hand lens on the end of its arm, so it could get up really close and get microscopic images of rocks. So this was designed to be truly exploration, so an exploration geologist, more or less, but in robot form. So these rovers were designed to follow the water. So Spirit was our first one, and it followed the water to Gusev Crater. So this is Gusev Crater over here, in this beautiful low-angle illumination shot of Mars. And what's special about Gusev Crater is that Ma'adim Vallis, which is this valley over here, this is a river valley that's as long as the Mississippi River. Thousands of kilometers, extremely long. And it empties into Gusev Crater. And as far as we can tell, there's no outlet. So this giant river network empties into Gusev Crater, and that water must have gone there. It didn't go anywhere else. So that implies there must have been a lake there, right? There's even, you can kind of see this sort of all this stuff down here might be a degraded delta. So this was the idea, that Spirit was going to land and see all these beautiful lake deposits containing all kinds of interesting microbes and organics and all kinds of cool stuff extending off into the horizon. All right, so one really difficult thing about landing a rover on Mars is that you can't quite land it like you would a lander. A lander, you have this big platform, you stick rockets on it, and you just basically hover down to the ground. A rover is much more delicate. It has wheels it has to drive on, so you can't land on those wheels. So you have to figure out a different way to land. So the JPL engineers did a great job at this. So here we have our rover tucked up inside this capsule, about to enter the Mars atmosphere, going very fast. And of course, once you hit atmosphere, you have a lot of friction building up, and that helps slow you down. There's a specially designed heat shield that helps that happen on the bottom of the capsule. So this parachute helps slow you down a lot, not quite enough. All right. So here comes the fun part. So this was the engineering revolution that the guys at JPL, or people at JPL, came up with, airbags. So we're going to land a rover inside a bunch of airbags. Extremely sturdy, durable, very well engineered airbags, but airbags nonetheless. So remember, we're in Mars gravity, about a third the Earth, so this thing is going to bounce for a very long time. And they did. And we can actually see the bounce marks that were left behind from satellite images. All right, so here's the really beautiful part. So where's the rover? The airbags deflate, and it opens like a flower. So here's our little rover, all tucked up inside, curled up like a cat, its little paws, tucked in. Again, I love MSL, but Spirit and Opportunity were just adorable rovers. I actually had a friend who did a study looking at how the ratio of eye sizes and things determines how cute we think things are, and the rover scored very high. Okay, so here it is unfolding its solar panels. So these rovers are both solar powered, got all their energy from the sun. And then we'll see it raise its mast and take its first images, and that's its antenna over here. There it goes, its wake. Okay, so that's how Spirit and Opportunity landed. So when Spirit landed, again, remember we were expecting this expanse of lake deposits, clear signs that we were following the water to this huge lake. This is what we saw. This is one of the first images that came back from Spirit. To the non-geologist, these rocks are lava. Everything you see in front of you is completely covered in a super thick layer of lava. So we have no idea from this image whether or not there was ever a lake here. All we see is lava, and that's a huge problem because these rovers were only designed to have 90-day missions, 90 sol. Sol is the word we use to talk about a Martian day. Martian days are about a half hour longer than Earth days. So this was pretty bad. We're going here to find water, and the petrologists, people who study rock, were delighted. Oh, rocks, this is great. We can go study all these lava rocks. People who wanted to find the water were a little discouraged, but they had a bold idea. Off in the distance, about 3 or 4 kilometers away, they could see this line of hills, which they named the Columbia Hills Complex, after the space shuttle Columbia, which blew up shortly before this. But these were 3 to 4 kilometers away. These rovers were designed to move at about 0.025 miles per hour, and they had a 90-day mission. So the idea of this thing going 3 or 4 kilometers was just obscene. It was crazy, but they decided to do it. So Spirit went on an epic journey. Here it is, traveling across these lava plains all the way over to the Columbia Hills. Its 90-day mission ended about right here. So it had an epic journey across these plains, visited a few impact craters along the way. To planetary geologists, impact craters are basically our road cuts. They tell us what's under our feet in the subsurface. So Spirit ended up here in the Columbia Hills, and then actually ended up down here in the middle of the hills. And what did it find? Well, first, actually, we should mention why the mission was only supposed to be 90 days and why Spirit was able to go so far. So the problem with Mars and solar-powered robots is dust. Mars is an extremely dusty place. Dust is just very constantly and slowly raining out of the sky all the time. So even things like the rover tracks you can see down here eventually get dusty, covered up. You can't see them from orbit anymore. That happens with the rovers too, but the problem is these guys are solar-powered. So this layer of dust on their solar panels is a big problem. And so the prediction was that after 90 days of dust raining down, these rovers would be non-operational anymore. They would get their electricity supply would get so low they wouldn't be able to start their heaters up at night, and they would get too cold and basically freeze up and die. Very sad. But this is after. This is the before. This is after. These rovers are self-cleaning. And here's why. This is a dust devil. So dust devils, we see them all over Mars. They create beautiful swirly patterns all over the surface. They're great at hoovering up dust. And one of these guys, actually several of them, ran right over the rover and sucked up all the dust off the solar panel. And so that's the only reason that Spirit was able to go so far, to able to travel kilometers and kilometers and kilometers into the Columbia Hills. So thank you, Mother Nature, for throwing us a huge bone. So this is in the Columbia Hills, where we're expecting to find, stuff that's at least not lava, right? That's the idea. The hills are sticking up out of the lava. If you were a geologist, you'd call them a kapuka, which is a great Hawaiian word that means the thing sticking out of the lava where the lava went around. And so that's what these hills are. They're kapukas. So here's what we found in the hills. They don't look particularly impressive. They just look like rocks. But when you can look at them and look at their mineralogy and their chemistry, which are very important for understanding the history of how water interacted with the rocks, because water interacting with rocks leaves behind diagnostic minerals that tell us how that interaction happened. Spirit found carbonates. So carbonates are things like limestone. You find them in Earth on the bottoms of seas and oceans. And here we found them on Mars. So these were basically a signature of what we think might be ancient lake deposits. At the very least, it's a sign of long-lived water in these hills and potentially an ancient lake. But Spirit kept going because it was an intrepid little rover. I went down into the middle of the Columbia Hills because from orbit we saw this really weird, almost like a diamond-shaped, light-toned plateau, which we called home plate, hopefully for obvious reasons. And when we got there, we realized it was basically a hole that had been filled with light-colored volcanic ash. But what's cool, oh no, sorry, malfunction. So this is one of the fortuitous things that happens in planetary missions. So Spirit had a broken wheel. One of its front right wheel just broke. It stopped turning early on. It wouldn't freewheel. It was basically the stuck wheel that wouldn't turn. Had to drag it around. So of course the engineer's solution was, all right, why don't we just drive backwards? So instead of trying to drive forward and push it through the dirt, they drove backward and dragged it behind them like a lame leg. And so what that did is it created this trough everywhere the rover went, just this trough through the soil. When they got to home plate, here's what they saw inside of that trough. All this yellow and white stuff, something clearly different. When they looked at the mineralogy and the chemistry of this stuff, they realized that the yellow stuff is salt and the white stuff is silica. These are minerals that only form when you have abundant water, high temperature water moving through rocks. So what we think that this is the signs of an ancient hydrothermal spring at this site. So we saw this volcanic deposits, and next to it we found signs for a hydrothermal spring like you might expect to find in a volcanic environment. So the analog for this that I deleted from my slide is Yellowstone. If you've been to Yellowstone, you've seen the beautiful colors, the white silica and all the crazy colored sulfates deposited around these pools. That's the kind of analog we're talking about for this. So a hydrothermal spring environment, extremely habitable as far as we know. So this was another huge success for the rover. But unfortunately, these salty soils ended up being the rover's demise as well. You can see it had a really hard time getting through it. And Spirit struggled along through all this stuff for a long time, but eventually it got to a point where they couldn't get out of these soft materials enough to tilt the rover toward the sun so that it could winter over, tilted toward the sun, getting as much energy as possible. And again, the problem with these rovers, they need their electricity. If they're not getting enough sun, they'll not be able to power their motors, they'll freeze up and they'll die. And unfortunately, that's what happened to Spirit. So Spirit froze up. Never heard from her again. We do call them hers. They're hers to us. So Spirit rover lasted from 2004 to 2010, completed 2,251 sols of her 90-sol mission. And this is one of my favorite pictures from the Spirit mission. This is actually what a sunset on Mars looks like. It's blue, not red. Okay, but we said there were two rovers, right? Spirit and Opportunity. Why? I mean, NASA doesn't usually get two of something. NASA usually barely gets one, so why were there two? Well, right around this time, there was a pretty spectacular discovery made. Right before this time, we had figured out that some of the meteorites we have from space are actually meteorites from Mars. These are rocks that are blasted off the surface of Mars when another big asteroid or something hits the surface, blasts them off into space, and a few of those will actually hit Earth. So we have a few very precious samples of Mars that came to us through space this way. It took us a while to figure out these rocks are from Mars. It turns out there was one actually sitting here in Purdue in someone's desk drawer. We call it the Lafayette Meteorite. Once we figured out it was from Mars, it became extremely valuable. But here's the one that matters, and every planetary scientist can tell you the name of this meteorite. It's ALH 48001, found in Antarctica. Now this meteorite, when people carved it up and started looking really closely, here's what they found. Very strange morphology is the word we'd use. Very strange little tubular structures. On Earth, when you see this kind of thing, you would say, oh, that's microbes. That's a tube left behind by a microbe. It's basically microbe poop, mineralized here. So what is this that we're seeing in the Mars meteorites? So of course the announcement was life on Mars. You know, President Clinton got up on TV and said, oh, we found life on Mars. It's, you know, blah, blah, on and on. But the consequence of that, even though we weren't sure what this was the White House gave NASA a call and said, hey, I heard you're sending a rover to Mars. Do you want another? To which NASA was like, yeah, totally, give us that second rover. So, you know, now that we've had more time to study this meteorite, we're not sure what this is. This looks really similar to microbial signatures on Earth, but it's a lot smaller. So it could be abiotic is the word we'd use, not from biology. So that's a very controversial subject still. But that second rover turned out to be the Opportunity Rover, and so we could pick another site on Mars to send this rover to. So we sent it to Briony Planum, which here we're showing. This is a pretty big area. This is, you know, hundreds of kilometers across. You might be saying, well, why here? That looks really boring. And it is to a normal geologist. But I'm not a normal geologist. I'm actually a spectroscopist. And so what I do is I study the surfaces of other planets using different wavelengths of light. So if you look at, you know, a mineral and look at it in the visible, it's just brown or whatever, something boring. But if you look at it at other wavelengths, it absorbs light depending on what it's made out of. And so we can plot that up as a spectrum. Here we're looking at the reflectance of crystalline hematite, which is the really shiny metallic stone you often see in like gift shops. It's usually magnetized. This is what it looks like in a lab as a function of wavelength. So wavelength across here, basically it's darker at some wavelengths than at others. But we can take these laboratory spectra, we can compare them to spectra we take from orbit of Mars. And here's a spectrum of Briony Planum right here. So you can see that it looks really similar to the hematite. So this was an indication to the spectroscopists like me that what we were seeing in Briony was actually hematite-bearing plains. And hematite is special because, again, it's one of these minerals that only forms in the presence of water, usually a lot of water. We find it all the time in deserts and in soils and all over the place. So this was a mineral signature saying there had to be water here. This is not covered in lava. There is something here at the surface that once interacted with water. So this is a totally different way to study the planets. You know, until this point, spectroscopy of Mars had been kind of sketchy. You've been like, really? Can you do that? But this vindicated our efforts. So Opportunity landed in Briony in 2004 and is actually still going strong 4,000 sols later. Opportunity was the first robot to run a marathon at 26 miles earlier this year, just in August actually. It's traveled 26 miles at 0.025 miles per hour. So it's gone a long way in all those years. So, but when Opportunity got out and looked down at the surface, didn't see lava. Instead, what we saw was this. So all of these little blue balls, which the team affectionately called blueberries, These are pure hematite, and it's just littered. The surface is completely littered. Here we're looking at this is sort of like a meter or so square, so just looking down at the ground pretty much. It's covered in this hematite. And it looks like what's happening is that these things are actually embedded in this light-toned rock out here. We think this is actually sandstone, and they're just eroding out and just covering the surface. So here's what they look like close up. Little blueberries. When they get collected in a bowl, we can analyze them. We call it a berry bowl. But so here's the idea. We think how these formed is that you had a really sandy desert with sand blowing around and sand dunes, but that the water table in this desert was constantly fluctuating up and down and up and down. And as it did that, it deposited out these hematite blueberries inside of the sandstone. So again, water. We found water. Opportunity followed the water, and it found it. It's a mission success. An Opportunity, again, is still investigating today. It's traveled 26 miles, and it's investigated multiple craters. It's actually now investigating some really ancient stuff dug up by really big craters on Mars. And we're still getting science back from it. So that was a pretty good investment, I would say. All right, but those are the Mars exploration rovers. Their mission was to follow the water, and they did that in spades. They did an excellent job. But, of course, the next step after that is not just water, it's habitability. So that was the goal of the Mars Science Laboratory Curiosity, which is currently roving around the surface of Mars. Here's a great animation showing Curiosity. This thing is a beast. There is nothing cute about this rover. It is a beast. It's the size of a Humvee. It's big. It's burly. It can climb anything. And it has a laboratory to boot. Where the Mars exploration rovers were robotic field geologists, this guy is a roving lab on wheels. The interior, most of the cost, this is a very expensive rover, and most of the cost of that is on the inside, under the hood. This rover has the capabilities of a very capable geology lab like we have here at Purdue. It can take a rock, smash it up, and look in detail, look at the parts per million for organics by sniffing out the gases that are emitted when you burn up those rocks. It can look at the mineralogy to very fine scales. The stuff on the end of the arm this arm is the size of my head, and it's wielding around on this little super long arm. It has an imager. It has all kinds of cool things on the end. So it can do lots, this rover. It's extremely capable. So, but what does habitability mean? When we talk about Mars, usually we talk about habitable environments. That basically means it's an environment that has water and some kind of source of energy. But it's a really broad term. There basically isn't an environment on Earth that is not habitable. Here we're looking at, these are the acidic waters of the Rio Tinto in Spain, highly acidic, like pH 1. There are microbes living in this. They get their energy from those acidic reactions. This is a nice swampy wetland, probably what you think of when you think of a really habitable environment, flush with life. Here's the Atacama Desert. It's a great Mars analog because it's super dry. It's not a great Mars analog because if you turn over one of these rocks, you'll find microbes underneath. So these are all habitable environments. So when we're thinking about Mars, it's not just habitability, but it's also what makes those environments habitable. What are the chemical reactions the microbes are using? Is it photosynthesis from the sun? What's going on in these environments to make them habitable? And so that was Curiosity's goal, to investigate, to find a habitable environment and to investigate what made it habitable. So Curiosity is currently seeking out habitable environments inside Gale Crater. And in particular, Gale Crater was chosen as a landing site for this very important mission because of this. This is a 3-mile-high mountain of sediments inside of Gale Crater. This is as high as the Grand Canyon is deep. And it's basically a series of sedimentary layers or rock layers just like the Grand Canyon. The Grand Canyon is one of the best records of geologic history in the southwest US. This we also expect to be an incredible record of Mars geology. Just for perspective, here's where Curiosity landed. And here you can see that mountain again. This is a big crater. We're talking over 100 kilometers across. So here's what that mound looks like from the ground, from the rover. So you can see sand dunes, dark basaltic sand dunes all along the base, and all these layers going all the way up. Again, 3 miles. More layers over here. And this is what Mars sky actually looks like if you white balance it correctly. It is actually blue if you look toward the horizon. All right, so that's the mound. Curiosity is destined to climb. So here's a close-up of some of those layers, and this is what gets geologists really excited, is layers, layers, because layers tell us that there is a record here. There's a record of how the geology of the surface changed over time. And in particular, why we're excited about this mound is because it's not just layers of sediments. These sediments have different mineralogies, And again, minerals tell us about how water interacted with rocks, what the chemistry of that water was, what the environment was that was there. You know, the minerals deposited from that acid river, that swamp, and the Atacama Desert all look completely different, and we can use the minerals to figure out how they were different. So when we look at the mound, we see clays like you'd find in the soil in your backyard. We see oxide like the hematite that we found at Briony, and we see lots and lots of salt. So these are all things that form when you have rocks interacting with water. And they're all different. That's the key. So as we go up this mound and travel through these layers, we're traveling through time and evaluating different environments and how they changed over time. Okay, so Mars Science Laboratory. This was a big rover. It was too big to land with airbags. It would have popped the airbags. So they had to come up with a completely different way to land. And here, again, the next problem was that this rover was so big and it required huge retro rockets to land, the rockets that prevent you from hitting the ground once you get close. And those rockets were so big that they would be blasting rocks and sand and pebbles and stuff all over the place to the point where it would probably damage the rover and damage the instruments. So they had to come up with another ingenious solution that gave all the scientists heart attacks, and we heard about it. All right, so here's MSL and its capsule entering the atmosphere. So we call this time period between when MSL enters the atmosphere and when it gets out of this sort of fiery hellhole it's in right now, the 7 minutes of terror. There are 7 minutes between when it hits the top of the atmosphere and when it can communicate with Earth again. So back here on Earth, that is a nerve-wracking 7 minutes because you don't know if this thing has exploded for quite some time after it's hit the atmosphere. Okay. So this parachute is the biggest parachute ever designed. They had to design an entirely new kind of parachute to land this thing because it's so big and because the atmosphere is so thin. So here's the rover tucked up underneath. We lost the heat shield. So this parachute, again, it didn't quite slow things down enough, and so they had to get rid of it. Chop it off. All right, so here it is, MSL descending on its retro rockets. But again, you can't let these get too close to the ground because it'll kick up all that sand and rocks and damage the rover. So the engineers developed what they call the sky crane. So we have actual descent imagery that I'll show you in a minute after we do this. Actual HD video of the landing. All right, so this is the sky crane. We're going to lower the rover on strings to the ground. Gently lower it. But at some point, you have to cut the strings. All right. So this guy, obviously, it can't stay around. It's really dangerous. So you cut the strings, it flies off, and it explodes. So in the descent imagery, I don't think we can see it in the part we're going to watch. But you can actually see the flash of explosion from this guy going off and hitting the surface. All right, but here's MSL already sitting on the ground. All right. MSL, the next day, it'll actually wake up, put its mast up, do some initial tests. It took this rover was so complicated and the instruments were so technical, it took months to test it before we could really get moving. So that was frustrating to the scientists, but that's the payoff that's the cost for having these really, really useful instruments on Mars. All right, but here's the actual HD video from the bottom of the rover. So what we're going to see is this is actually the heat shield flying off. You know how we saw the rover exposed underneath the capsule? This is a video from the belly of the rover. Yeah, so that you drop the heat shield so that you can let the rover come down. So that's all entirely, this went perfectly according to plan. Scientists are all so impressed because it seems crazy. All right. So here we're going to see the heat shield fly off. So we're with the rover inside the capsule. You can see this is atmospheric entry, all that burning you can hear. There's the heat shield flying off, and here's Mars. This video I just love because this is what it looks like to actually land on another planet. So here you can see the dunes down here. This is Mount Sharp, the giant mountain in the middle of the crater over here. You can see the winds buffeting the capsule. You can see all this stuff on the surface. This is what it would look like from a spacecraft landing on Mars. So you can start to see how interesting this geology is, right? There's all this stuff going on, all these holes and windows into the underlying stuff that geologists get really excited about. These dunes are helping to erode some of that rock away and expose the underlying rock. And these videos are all online. If you just Google, MSL landing animation or just MSL like HD video landing or something, you can get these online. All right, we're almost down. So that the sounds are real too. There's a microphone on board MSL that records the winds, it records the sounds, which is actually, it's not a science instrument. It was put on as an outreach instrument to record the sounds and play them back to the American public. And that was actually organized by the Planetary Society. All right, so here we go. So now we've been dropped from the capsule and we're descending with our retro rockets. There's a wheel. And so at some point, if you keep watching, this was a flash, and that's the other guy going off and exploding. All right, so that's what it looks like to land on another planet. So cool. And that camera is still on. It's actually been taking images of what's underneath the rover as it drives along through the whole mission. Not quite as exciting as landing, though. All right, so here's a picture we actually got from space from one of the best camera we've ever sent to another planet, the HiRISE camera. On one of NASA's satellites. This is, you can see the parachute here, and this is the capsule. So this was an incredibly difficult image to get, but we got it. All right, so here's Curiosity on the ground. This is my favorite Curiosity selfie because it's been on Mars for a while, and it's getting kind of dirty like a geologist should out in the field. But you can see, this is actually a nuclear-powered rover. This giant butt back here is actually its RPG on the back. Or, sorry, RTG, not RPG. That would be awesome. Not a weaponized rover. Okay. Oh my God, do this again. All right, so this is where Curiosity landed. So here we're looking at topography or elevation. So blue is low, red is high. So the goal of this mission was to get to the mountain, which is down here, way down here off to the right. But it turns out there was really interesting stuff at the landing site as well. So here's the rim of the crater up here. Crater rims are basically the mountain chains of Mars. They're huge mountain chains that just happen to be circular. And here's a valley coming out of those mountains. And at the bottom of that valley, there's a huge fan, what we call an alluvial fan. On Earth, you get these in deserts when you have mountain valleys emptying streams out onto plains. And they basically get out of this valley and dump all their sediment and produce a huge fan. So we weren't really sure what we'd see when we got here. Would we see this fan? Would we see pebbles? I don't know. This is what Curiosity saw when it looked down. So these are nice rounded pebbles all over the ground that are lumped up in what we call a conglomerate. This is what river sediments look like on Earth. So Curiosity landed on river sediments on Mars, on pebbles, river pebbles on Mars. So this was already vindication that we went to the right place because we're already landed on a habitable environment. So Curiosity kept going and started digging around. This is a drill hole for Curiosity. And when it started drilling around, what it found was this stuff, all this sort of grayish green stuff. Note how different it is in color from red Martian dust. That means it has a fundamentally different chemical composition. In fact, this is sort of like oxidized iron rust kind of stuff. This is reduced lake sediments is what this is. So it actually contains organics. This is the first positive detection of organics on Mars. Very exciting. Lots of clays, the kind of minerals you'd expect to find in lake sediments. So Curiosity not only found a river, it also found a lake pretty soon after landing. So that's very exciting. So this was clearly a habitable environment. And by studying the chemistry and mineralogy of these lake sediments, we can learn more about how microbes might have lived there. So Curiosity, though, remember, it's not capable of detecting life in and of itself. That has to come later. But it was trying to detect a habitable environment, and it already did that before it even got to this awesome mountain it was trying to explore. So Curiosity kept going. Here it is sort of in progress. It just climbed a sand dune and looked back. So traversing, we have to try to get around this giant stream of sand dunes here to get to the mountain, which is over here. And so Curiosity is currently doing this. But this green star is a very special place. And this green star looks like this. So all these tilted layers in here are really interesting to a geologist, Because what those are deltas. It turns out Curiosity had been driving over a series of lake deltas as it drove this direction. So the idea is what we're seeing is a lake that kind of came and went. It was there, it laid down a delta, it went away, it dried up, it came back, laid down another delta. So lots and lots of lakes building up over time. Here you can see sort of, snow-capped, icy peaks down here. It's dried up. You get a really wet season. Lots of water comes off these peaks, deposits out this lake, makes a big delta, and so the delta grows this direction. So that's what Curiosity was seeing. So it's found a river, it's found lakes, and it's found a delta. So it's sort of the holy grails of Mars exploration. But it's still going. Curiosity is still actively working on its mission, and it hasn't even gotten to the mountain yet. It's really just getting to the base of it now. This is where Curiosity is now. It's just about to encounter these dunes. It'll be the first time we've seen a dune up close on Mars, and I study dunes, and I think they're beautiful and fascinating, so I'm very excited for that. But Curiosity is still working on it. Here is a recent view from earlier this year showing Curiosity's current terrain, more or less. So you can see it's lots of valleys and lots of sand. It's pretty tough terrain to traverse, and it's actually taken a really nasty toll on the rover wheels. Everything on this rover is super lightweight because every ounce you add to the rover itself, you take away from a science instrument. So you try to keep these things lightweight. Unfortunately, the wheels were a little too lightweight, so they've been kind of eaten up by these rocks. But it's still going. Curiosity is trekking onward, excited to get to that mountain. But what's next? Next is Mars 2020, and this is a really exciting part. Purdue is going to Mars in 2020 with the next rover. So the Mars 2020 rover is the next step, and it's going to search for biosignatures. It's actually going to Mars to search for life. And more excitingly, it's actually going to Mars to collect samples that we will eventually bring back to Earth. And we're very excited that me and my students will be part of the science team as part of the camera instrument on board Mars 2020. So that's a big get for us, and we're really excited. Okay, but what is a biosignature? So we said we followed the water, we found habitable environments. Now we actually want to look for life. And the way we look for life, we're talking about microbial, very, very small life, is we have to look for biosignatures. And this is the same thing we do when we're trying to understand life on the early Earth. You get rocks dating from very, very far back on the Earth, and you look for biosignatures. Things like microbial fossils. This, of course, is the best kind of biosignature you can find, but they're pretty rare. Instead, you can try to look for ways that life has altered the chemistry of stuff around it. So you can look for, organics. Organics by themselves aren't necessarily biosignatures. They form inorganically as well. But life gets in there and messes with them and leaves behind diagnostic signatures. Things like structures, interesting chemical isotopes, geochemistry. Here's a really interesting one. So these are two different types of proteins. It turns out when life gets in and starts messing with proteins, it only likes left-handed proteins. So proteins that sort of go this direction. These are basically the same molecule. They just have a slightly different orientation. But life really likes this one. So when you have life in a system and you look at this protein, you basically see like 99% left-handed proteins versus in a normal, inorganic system, you'd expect to see an even distribution. So that is one really interesting biosignature. So with Mars 2020, so we can't really look for microbial fossils on Mars. That's really hard. We can't look for a lot of these really detailed things. We really have to bring those samples back here to Earth and look at them with our super fancy giant instruments and labs here on Earth. But we can start to at least triage samples with the Mars 2020 rover. So this rover, it looks really similar to MSL. It's the same chassis, but the instruments are totally different. My students and I will be on the camera team, MassCamZ, doing a lot of the in-situ geology with the rover. But we have instruments that will be looking for organics. They'll be actually imaging rocks and looking at where the organics are concentrated. We have instruments looking at chemistry, looking at mineralogy, all these things all together. So right now, launch isn't until 2020, we have a few years. So right now we're building the instrument, assembling the rover. We're also trying to figure out where to go. What one place would you go to on Mars to look for life and to collect samples, potentially our only actually well-categorized samples of the Martian surface? If you were going to go to Earth and get one sample to understand the history of Earth, where would you go? It's a really hard question. And so it's one we're trying to figure out right now. It's a community-wide effort. We're holding workshops. We recently held one last month with the whole Mars community. And we actually got our selection down to 8 different landing sites that we're considering for Mars 2020. They sort of fall into a couple categories. One of them is actually the Spirit landing site with that hydrothermal spring. We might go back there and get some of those samples. We also are looking at a lot of them are actually deltas, just like Curiosity is driving over now, but bigger, better deltas, older deltas. We're also looking at places that have subsurface environments, subsurface hydrothermal systems. We're looking at places that have records of surface environments, sort of whole soils and rivers and lakes. So we're looking at all these, thinking about them, trying to learn about what we would find if we went there, and it's going to take a while, but we'll get there. It'll be a lot of arguments, but we'll figure it out. So just to clarify, Mars 2020 itself isn't going to return the samples. Mars 2020 will find the samples, it'll extract them, it'll cache them all together, and it'll basically leave it on the surface, waiting for basically congressional funding to say, hey, yeah, we should go get those samples we spent so much time and money collecting. And so eventually we'll send another mission that'll have a really stripped down, very basic rover that can go get the cache and bring it back to a launch vehicle. Now this is the really hard part. We've actually never launched something off of the surface of another planet. We've been to the moon and back, but the moon has so much less gravity, it's so close to Earth, it doesn't really count. So this is really hard, and it turns out this is probably the hardest part, and it's the thing we need to do before we can send humans to Mars. There are some people that say that before we can go to Mars with humans, we have to get a sample to make sure there's nothing crazy, toxic, or viruses, or who knows what, space viruses, I guess, that would damage our human crew members. But the other thing too is that this is a really basic technology development process that we need to do before we can send humans. So that brings me to human exploration of Mars. So NASA does view these rovers as a key component of getting humans to Mars. So lately they've been advertising this as the journey to Mars, and actually using this as advertising for the upcoming movie The Martian, released October 2nd. NASA is full force behind this movie. It's getting great reviews, and the book was amazing. So please go see that. But that movie is all about an astronaut on Mars and how he gets off Mars. But that's this whole process. So down here we're showing the robotic side of Mars exploration. Down here is the human, and they really go together. You need to understand what's on the surface before you can send humans. But we are working toward humans landing on Mars. We're actually involved here at Purdue in helping to evaluate landing sites for humans on Mars. So here's an example of what we're calling an exploration zone for humans on Mars. So here's this is actually 200 kilometers across. And the idea is that the humans could explore any area within this zone. Their actual habitat where they'd be living is sort of down here. The zone needs to include interesting science we can do, again, looking for biosignatures especially, but also needs to include places that we can mine for resources. So we're actually doing a lot of work right now trying to understand what are the mineable resources on Mars. Where could we go to mine for water, for example? All these hydrated minerals formed in water could actually be a great water resource for astronauts. So we're working on that now. There's actually the first workshop where geologists are really discussing where humans should go is happening next month in Houston, and I'll be there. All right, so hopefully I've made the case to you that Mars is really important in the search for life, and that rovers have really gotten us a long way. And I'll leave you with this image, which I really love. All right, thank you, and I can take any questions. Oh, here's a microphone.
Can you go into a little more detail in the instrument suite on Mars 2020 and exactly how it's supposed to be identifying useful samples? I mean, you showed this one showing names and type, but didn't really go into detail about what they are.
So JPL just put up a bunch of descriptions online, so those are new actually, because these instruments were just selected earlier this year. So our team's only been going for about a year now. So what do we have on here? So we have, again, the camera system, which I'm on up here. We'll be doing the geology and taking these beautiful color images. We have a couple of different spectrometers called Raman spectrometers that are great for detecting organics. One of those is on the arm, which I don't know where that is in this picture, but so the arm will have a Raman spectrometer that can detect organics and minerals on it. On the mast, there will be a fantastic instrument literally called SuperCam. SuperCam will have a long-distance Raman spectrometer for finding organics, another spectrometer for looking at minerals, as well as a laser that it can use to blast the rocks apart, see what kind of light they put out as they're being blasted apart, and then figure out what they're made out of. So that'll help us get at the chemistry and mineralogy with that instrument. We also have a chemistry instrument on the arm to do really high resolution, sort of micro scale chemistry, and that'll work with that Raman spectrometer on the arm to help identify what the specific deposits of organics might be in those rocks and where we should drill and sample. There's also a really interesting instrument on here called MOXIE that will actually help us understand how to extract things like oxygen from the Martian environment. So it's actually funded by the human exploration side of NASA as sort of a test run of in situ resource utilization, as we like to call it. And we also have a radar on board, a ground penetrating radar that will help us image the subsurface as the rover drives along to help us look for water or other things in the subsurface. I think I covered it. Okay. But so it's a great suite, again, completely different from MSL. It really, other than the camera, which is high heritage from MSL, everything else is very different. And we're really excited about what it might find.
Yeah, hi. So I mean, like you had mentioned that like the second and the third mission to Mars, like they were like intended only to be only about like 90 sol or 90 like the Martian days. But like now that we've crossed it, you know, like way more than we expected. Like how does NASA like plan its resources and its people? Like how do you have enough people to manage those and the projects that were intended to do?
Yeah.
You know, if it was only 90 days.
That's a great question. So that's actually a really important point. So NASA, you know, it costs 0.02 or 0.2% of the federal budget. I think it's 0.02%. And all of that money is salaries. That is entirely salaries that go to, you know, scientists and engineers working at NASA centers, working at universities. Like here, I'm entirely funded by NASA. And so when we talk about the cost of a mission, you think, oh, that's the cost of the rocket or that's the cost of the, you know, nuclear stuff in the back of the rover. It's not. It's the cost of the people. And so when we talk about, oh, we need to cut $10 million from NASA's budget, that's a rover. That's the yearly operating cost of keeping one of those really simple, you know, 10-year-old rovers going on the surface. And so it gets hard. And as a scientist, you have to learn to try to balance that. Like, I don't know when this rover is going to die. The principal investigator of the MER rovers, Steve Squires, has been PI of these things for a really long time now, and I'm sure he'd love to do other things. He loves his rover, but I'm sure he'd love to do other science. And so it gets hard after a while to keep doing these. But we love that we still have it. Again, these rovers are still bringing back great science, finding new things. So as long as NASA will keep funding them, we'll keep sending them.
Yeah, so really quickly, so I'm in political science, so I'm curious about how much is the collection going to cost, so the launch to get the samples. And also, have there been any recent efforts by any member of Congress, either the House or Senate, to try to put that in a spending package?
That's a great question. So I don't remember the full cost of Mars sample return. It's a lot. It's basically the next two, it basically requires two missions because you have to have a spacecraft go to Mars, drop the rover, and then another one that has the launch vehicle, and then an orbiter that can actually come back to Earth as well, which we've also never had to do. That's totally new as well. So it ends up costing about the cost of Mars 2020 times 3. So each one of those steps costs as much as Mars 2020, which is, you know, $1 billion or more per step. So it's a lot. And that's why we can't really do it as one mission, because you really have to fund it one step at a time. And we don't have the technology yet. As far as I know, there are no efforts yet to fund that. Again, we're not launching and landing this until 2020 and then 2021. We don't expect to have samples in place until at least a year and a half after that. So again, funding for that will have to come at some point soon. We're designing the sample capsules so they can sit on the surface for a long time. You know, if we need to wait 15 years, we'd really prefer not to do that, but we could. And they'll be sitting waiting. They've already been sitting on Mars waiting for 4.5 billion years. So.
Any other questions?
Here's back too.
So you had a previous slide where you were showing the pebbles that you had found.
Yeah.
So the pebbles were formed by water erosion, right?
Yeah, exactly.
So do you have any idea from, I guess, because you'd had further erosion after it dried up from wind, right? Mm-hmm. Do you have any idea of how old that is since it's dried up?
Yeah, that's a great question. So actually something we're talking a lot about for looking for biosignatures is preservation. And one of the big ways that organics and biosignatures get destroyed on Mars is radiation coming from the sun, coming from space. It basically destroys organics and destroys the signatures you want to find. The way to protect against that is to bury it and leave it buried for until 10 million years ago and then erode it back with wind. And so this whole site that Curiosity is driving over has been eroded back. And so that's why we can detect organics. And so all this stuff is really recently exposed, which is really important. Yeah, so we actually do have dates. This is the great thing about MSL. The gas chromatograph mass spectrometer actually can measure exposure dates and actual dates. So we have a real date from the surface of Mars. We now know that the crater itself is about 4.1 plus or minus a lot billion years old, and we know that these things were exposed about 70 million years ago from basically cosmic ray exposure dating. So we do have real numbers now, which is really exciting.
Let's give Dr. Horgan another round of applause. Thank you.
Thank you.